Welcome to the second Ray Summit Connect. My name is Dean Wamper. I'm your host today. The subject is the road to AutoML. We've got 3 talks lined up for you on specific topics of hyperparameter tuning, optimizing BERT, which is a popular natural language processing model, and neural architecture search. I want to thank our community partners. 2 of our speakers are from SIGOPT and Determined AI, so we appreciate their help in promoting this event. The SF Big Analytics Speed Up in San Francisco helped a lot, as well as Stacks in Chicago, Slacks, and also Rise Lab, which is the UC Berkeley project that was actually the place where Ray was born. Let me also mention 2 upcoming events that we have. One is we're going to do some live training next week, actually a week from today, on reinforcement learning with Ray RLib. I'll be teaching that. Also, our next Connect event will also be on reinforcement learning. That will be July 8th. You can find out more information about both events and register for them at anyscale.com/events. A popular question. We will post the slides and videos afterwards, probably in a day or so. Check the anyscale.com blog. We'll post all the information there. And on that subject, actually, if you missed last month's Connect event with Michael Jordan and Jan Stojka, you can find the videos and slides from that event at a blog post that you'll find if you go to the anyscale.com/blog. Okay, so the way it's going to work today is our speakers actually pre-recorded their talks, and I'm going to play them one at a time. And if you have a question, go ahead and post it in the Q&A feature in the Zoom app. The speakers are standing by. They'll answer your questions, or some of them will just wait and answer with the live panel discussion at the end. So there'll be 3 talks, then the speakers will join me for a panel discussion. And Siri can be quiet now. Thank you very much. Also, we'd love to hear feedback about what you like about this, suggestions for topics we might cover in the future and so forth. And you can send us email at events@anyscale.com. And if you'd like to tweet about the event today, you can use the hashtag RaySummitConnect, or you could mention one of our Twitter accounts, Anyscale Compute or Ray Distributed. Okay, enough administrivia. Let me introduce our first speaker. Richard Liaw is a software engineer at Anyscale and the primary developer of the Tune library, and he's going to talk about distributed hyperparameter tuning.
Hi, my name is Richard. I'm a software engineer at Anyscale, and I've been working on Ray for a couple of years now. Today I'm going to be talking to you about hyperparameter tuning, which I think is machine learning's most expensive problem. Today, we'll begin with this talk by motivating the importance and highlighting the complexity of tuning model hyperparameters. Then we'll overview some of the state-of-the-art techniques for handling this complexity. And finally, we'll talk about Raytune, a library built on top of Ray for simplifying and scaling hyperparameter tuning. At the end of this talk, you should be able to leverage new algorithms and new frameworks to accelerate your machine learning workflow. So let's start by motivating the importance of hyperparameter tuning. We all know that deep learning is experiencing rapid growth and adoption. And this is not only happening in academia, which I've presented on the graph, but also in industry where more and more applications such as speech recognition and autonomous vehicles are leveraging deep learning. But let me tell you something. There's a dirty secret here. There's a dirty secret in that there's actually a lot of hyperparameter tuning that goes into achieving these state-of-the-art performances. Let's take, for example, convolutional neural networks. These are very powerful machine learning techniques and are attributed to many of the recent advances in computer vision. On the screen here, I've shown you actually one of the original designs of convolutional neural networks by Jan LeCun. After 20 years of research, we end up with AlexNet, which sparked this new wave of deep learning that we have now today. What's interesting is that if you compare the two, the basic idea of convolutional neural networks hasn't really changed. But what has changed over the last 20 years is that we've largely modified the shape of the neural networks and also the size of each layer. And these are essentially what we call hyperparameters. And these hyperparameters obviously make a huge difference in But what's making matters worse is actually two trends. We see that models are getting larger and larger, with the most recent OpenAI model containing nearly 200 billion parameters. Also, we see that these models are not only getting larger, but more and more complex. So to the right, we see a table of Roberta, which has 20 different hyperparameters that they had to tune just to get a well-performing model. What this means for us is that selecting the right hyperparameters in order to achieve state-of-the-art performance is going to take a long time and consume a lot of resources. But what's making matters worse is two trends that we see today. First, models are getting larger and larger, the most recent OpenAI model containing nearly 200 billion parameters. Also, these state-of-the-art models are not only getting larger, but also more complex. What this means for us is that selecting the right hyperparameters is simply going to take a long time and also consume a lot of resources. So we arrive at the main problem of hyperparameter tuning today. It's not simply that how do we choose these hyperparameters, but rather how do we choose these hyperparameters in a way that is both efficient and fast. And today, in this talk, we'll cover a two-pronged approach to this problem. First, we'll leverage advanced algorithms to navigate the search space. And second, we'll find out how to use cutting-edge software to better leverage our compute resources. So let's cover three different tuning techniques on how we can efficiently navigate the search space. We'll cover random search, we'll cover bandit-based approaches, and then finally we'll cover population-based training. Some of these techniques might be applicable across all machine learning, including non-deep learning regimes, but some of these techniques will have much more significance and exploit different characteristics, allowing it to be much more impactful in the deep learning problems. So let's start off. Before we start, I want to make sure that we're on the same page about definitions, and I'm going to be using the word trial quite often. And that's just simply going to mean one hyperparameter evaluation. So one set of hyperparameters that we're going to sample from. So random search is just what it sounds like. Given different distributions of each hyperparameter value, we're going to sample parameters from these distributions, all of them at once, but over and over again, eventually aiming to find the best model. So when I say trial, here I mean I'm going to sample once from alpha, once from the distribution given to hidden layers, and once from the distribution given to params, as you see on the pseudocode. So now that I have sampled values from all three different hyperparameter distributions, I have what we call a trial. Now there's a couple benefits for doing hyperparameter search. First, all the trials are easily parallelizable since all of them are independent from each other. And also it turns out in high dimensions, random search is just very hard to beat. But what's wrong with random search? Well, it turns out there's a lot of things that we can do better. After all, you're only trying things on random. So I'll show you on the next slide how we can actually achieve better performance by limiting the amount of resources that we spend on bad trials. So for example, let's take this graph of training run accuracies. What we see on the graph is that there's simply a lot of models that are bad performers. Naturally, you can ask, well, why bother wasting resources on the trials that aren't simply going to be good? And so there's a hyperparameter tuning technique called bandit-based algorithms that addresses this precisely. So Hyperband and Asha are early stopping algorithms or bandit-based algorithms that aim to allocate resources to better performing trials. The intuition behind these algorithms is that each trial is going to be evaluated, and we're going to compare the relative performance among different trials at different points in time. At any point of evaluation, we're going to terminate the bad performing trials, and then we're going to let the better performing trials run for a longer period of time. Here's what this looks like in pseudocode. We're going to start with the trial, which is going to sample from, which is going to be, sample from some hyperparameter space. Then the trial is going to run for a number of epochs, and at a user designated cutoff for a period of time, we're going to evaluate whether or not it's one of the better performing trials. If it is, we're going to let it run for a longer period of time. Otherwise, we're going to pause it and allow all other trials to start. I also want to note that there has been many recent advances that have been made that have made Hyperband capable of being combined with smarter techniques such as Bayesian optimization. Another benefit of Hyperband is that it's easily parallelizable, meaning that you can easily increase its efficiency by leveraging parallel resources. But I want to also point out there's also much more room for improvement here. Turns out in deep learning, hyperparameter schedules matter a lot. This means that you can change the hyperparameter value during training, and this hyperparameter value can be something like momentum or learning rate, and you can actually affect the performance of the model simply by perturbing the hyperparameters during training. This is actually required in a lot of models to achieve state-of-the-art results. So there's a technique called population-based training that addresses this issue. This is a technique that was published a couple years ago by Google DeepMind. So the main idea of population-based training is to evaluate multiple trials in parallel, and at a certain frequency, similar to Hyperband, terminate the lowest performers. But when we terminate the lowest performers, instead of starting a new trial, we're going to copy the weights of the best performer and mutate its hyperparameters so that we can search across different schedules. A quick walkthrough of this code shows that, or let's take a quick walkthrough over the example. So we'll start off with 4 different hyperparameter values, say 0.1, 0.2, 0.3, 0.4. And we're going to run each of these different trials for just a set period of time. After the set period of time, we're going to evaluate all of these trials, and we'll find that 0.4 is actually performing very poorly. So let's terminate that, and instead let's take the best performing trial and copy its weights and mutate its hyperparameters. So 0.1, what turns out was the best hyperparameter, or the best performing trial. So we perturbed its hyperparameters to 0.15, and we copied its weights and effectively cloned a copy of 0.1 to take the place of 0.4. And we'll do this over and over again. So in this case, let's say 0.2 is the worst performer and 0.3 is the best performer. So in this case, we'll terminate 0.2 and we'll perturb the weights of we'll perturb the hyperparameters of 0.3, copying it to take the place of the terminated trial. So the benefits of population-based training is that it's actually easily parallelizable. It also allows you to search over different hyperparameter tuning schedules, which is important for achieving state-of-the-art results, and it is also efficient in that it terminates bad performance. Now you might be asking, well, okay, does this really work? Well, Google DeepMind ran this technique over multiple published algorithms when they first released this algorithm, and they found that across the board, population-based training was able to provide non-trivial performance increases over the state-of-the-art. So now that we know about the state-of-the-art in hyperparameter tuning algorithms, how do we efficiently leverage our resources so that we can tune our hyperparameters quickly? Well, Raytune is a library that addresses this problem. It is a scalable hyperparameter tuning library built on top of Ray. So to give some context, let's quickly talk about Ray. Ray is both a framework for distributed Python, but also contains an ecosystem of libraries for specific use cases, such as Raytune. How do these two interact? Well, Raytune actually leverages the primitives that Ray, the framework, exposes so that Raytune can easily parallelize and distribute its work across multiple nodes and cores. So Tune specifically is a library that handles the execution of hyperparameter search. It provides hooks and plugins for different hyperparameter tuning algorithms while automatically handling the parallelism for you. So why is Tune special? Well, Tune is actually built with deep learning as a priority. This means that Tune is built so that you can effectively utilize and spread your training across multiple GPUs. You can also tune different models built with any machine learning framework. And finally, Tune allows you to run hyperparameter tuning at any scale. And you can go from running a single process to running multiple GPUs to running across multiple nodes, all without changing your code. Tune also offers many algorithms to optimize your hyperparameter search, including all the hyperparameter search algorithms mentioned today. Tune also integrates with many hyperparameter search libraries, such as Hyperopt, Axe, or SIGOpt, allowing you to transparently scale these libraries across multiple cores and nodes. Now, Tune is actually quite easy to use, and let's walk through an API demo real quickly. So let's start off with a simple training function. This is very similar code to something that you might see in Keras or PyTorch. And all we have to do to convert this to using Tune is by adding a report, a one-line call to report the loss or report some accuracy metric. And this notifies Tune to inform Tune of the current intermediate result, the intermediate training progress of this training function. To run a search or to use Tune, you can actually just simply call tune.run. And if you want to run a search of different hyperparameters, you can easily specify a search space and add a single argument, which here is num samples, and it allows you to run up to 100 different samples from this hyperparameter search space, parallelizing them to leverage all the cores in your cluster. Tune also provides a lot of other features through this API, such as checkpointing and different search algorithms. Finally, if you want to tune something like BERT, which is, as we know, very large and very complex, you can easily speed up the tuning process by enabling the trials themselves to be distributed. This requires the usage of an underlying framework, and Ray actually provides many of these frameworks for you to leverage in different use cases, such as RLib for distributed reinforcement learning or RaySGD for distributed deep learning. So by using Tune, you can simplify the execution of your hyperparameter search, ultimately accelerating your machine learning workflow. To summarize in this talk, we motivated the importance and highlighted the complexity of hyperparameter tuning. We overviewed some of the state-of-the-art techniques for tuning parameters. And finally, we talked about Raytune, which is a library built on top of Ray for simplifying and scaling hyperparameter tuning. I hope that the information presented in this talk you can actually take this information and accelerate your existing machine learning workflow. So thanks for listening. And if you have any more questions, you can feel free to reach out to me on Twitter or at my email. There will also be a panel section later on, and happy to take any questions there.